Hey everybody, this is Mike Heumann and welcome to the G2M Research Multi-Vendor Webinar on Edge Computing and Storage, how to get and keep your data off of my cloud. I'm going to introduce the topic and talk a little bit about the ground rules, and then we'll turn it over for some short presentations from each of our different vendors, and then we'll go into some audience survey questions and key questions. And finally, we'll do the audience Q&A at the end of the webinar. If you have Q&A, please use the Zoom question and answer window. Put those in. You can put them in whenever you want. We'll hold them until the end of the webinar, and we'll go ahead and answer them then. This webinar is being recorded, and we'll make the recording and a copy of the slides available to everybody who registered for the webinar. Those notices will get sent out probably tomorrow or Thursday, so be looking for that at, say, 48 hours from now or so. And with that, let's jump right into it. So I'm Mike Heumann. I'm the managing partner of G2M Research. Our panelists today are Josh Goldenhar, VP of Product Marketing from Lightbits Labs, JB Baker, VP of Marketing from ScaleFlux, and Scott Shadley, VP of Marketing from NGD Systems. So I think we all know that the Edge has lots of data, and the amount of data that's generating is just growing exponentially over time. There are some estimates that Gartner's recently done that says 75% of enterprise data will be stored and processed at the edge within 5 years. That's not too far away. That 90% of industrial enterprises will utilize edge computing by basically 2 years from now. That's Frost and Sullivan. Because of all that, the edge computing market is expected to grow almost 20% a year between now and 2025. And it's expected the companies will spend roughly about $200 billion on IoT hardware by 2025. So this is a huge market. It's a huge problem. It's a huge area that there's a lot of opportunity for innovation. You know, so if you think about it, the biggest problem you have at the edge is you've got lots of data, and you oftentimes have pipes that are not quite big enough to move all that data. You know, if you think about, say, an aircraft engine management system, say for a Boeing 777 or an Airbus or something like that, or self-driving vehicles or video surveillance systems, these things can generate terabytes of data per hour. Obviously, in most cases, you don't have a pipe big enough to move all that data. So, you know, what are the options to really deal with that data? Because if you can't do something with the data, obviously, the value is very limited. The first one, pre-processing the data, only moving the metadata, sampling data. There's various data compression approaches. There's data processing while the data is in place, also known as in-situ processing, or combinations of all of these things. Those are some of the areas that our panelists are going to talk about. So with that, let me pass it over to Josh Goldenhar. Again, Josh is VP of Marketing at Lightbits Labs. Josh, go ahead and take it away.
Thanks very much, Mike. Good morning, good afternoon, good evening to all of you out there, and thanks for spending some of your day with us. So we will go ahead and talk a little bit about what does it mean, data at the edge or cloud, edge cloud, you can call this what you want. But really, if you see this, this kind of fun depiction of the Earth here, what we're talking about is if you imagine you're a spaceship out here at the edge of the Earth, and you want to talk to the cloud data center, you want to send your data back there for what you're doing in your survey, it's a very long distance. And because of physics, it just means there's a lot of latency involved. Also, we know, Mike had mentioned, airplane, aircraft control systems. If anybody who's used the internet on a plane, back when we used to fly, knows that, the internet can be quite slow from an airplane, so you're bandwidth limited. And if you've used the internet on an airplane, you also understand the issues of latency and distance, because it's bouncing up either to a satellite or to ground stations and coming back. And so imagine, even farther when your spaceship is out at the edge. Latency can be a real issue. And if you're using data out at the edge and you're trying to make a decision on that, like an AI decision, or some kind of automated process that's looking at the data almost in real time or at real time. If it takes a really long time for the data to go, be decided on, and come back, it hinders your decision making. So data at the edge often when you wanted to process it in real time and make decisions, it just doesn't work to go all the way to the central cloud data centers. I talked about limited bandwidth already. We can't necessarily send all the data. Mike mentioned that as well. And also we have what I'm kiddingly calling galactic regulations. This is local regulations may not permit the data at the edge to be stored in a central location. Obviously, this is usually down to privacy concerns and local laws. So then what does storage at the edge get you? So you put some of the storage or all of your storage at the edge, maybe in multiple edge locations. Usually this is still going to have some kind of connectivity to the centralized cloud, to centralized data centers. And now when the edge storage is very, very close to where you're actually sending the data in or you need to analyze it, your decisions can be made very quickly. Latency is very low. Local bandwidth at the edge, that is between the storage device and your spaceship or your medical imager or your manufacturing plant, the local bandwidth is usually going to be very high, higher than the bandwidth to the central cloud. And with your regulations there, same kind of thing. Regulations are going to basically favor where the data is created to stay in that locality. So this solves a lot of problems to have storage at the edge. So now let's not just do these kind of fanciful things. Let's talk about really what's driving data to the edge. So I mentioned this a little bit, latency sensitive applications. Some of these were mentioned as far as if you really think about the classic example is cars, and automated traffic systems of the maybe not so distant future. These things require very, very fast response times. You can't have the data go all the way to a cloud data center, get processed, and then come all the way back. They need to happen at the edge. They can't tolerate the high latencies there. So you just simply for latency sensitivity, it has to happen at the edge. You also have to deal with cloud egress bandwidth reduction. And what in the world do I mean by that? That is, if you think about a CDN, if you think about a very classic use case, that's all of us streaming Netflix movies. If all the data, if all the streaming was coming from a centralized location, you'd need a massive amount of bandwidth going out of the central data center. So you don't do that. Files are cached in edge locations, content distribution networks. So you put those Netflix movies at the edge, closer to the users, and then you've got much more aggregate bandwidth because you've got the aggregation of all the different little data centers at the edge. And finally, cloud ingress bandwidth reduction. Same kind of thing in reverse. If you have tons of data out at the edge, we're seeing more, a classic term, of course, is IoT, Internet of Things, all these things sending in data. If it's a wearable, if it's a camera, if it's some other kind of sensor, it could be on a Coke machine. When you have all these things sending in data in aggregate, you need massive amounts of bandwidth into the data center, which simply may not be practical. So it's much better to have those edge devices talk to something that's local, where they have more bandwidth, and then you have the aggregation of all that bandwidth at the edge. Finally, what also is driving it? A limited connectivity. Edge devices often don't have a lot of cloud connectivity. Again, think back to the airplane scenario. You're on the airplane, you've got an internet connection, and you're trying to use it, and sometimes it just kind of goes away, or it's very slow. So if there were critical data happening on the airplane, you want it to be processed, the airplane itself could become a mini edge cloud or edge data center. Security, sometimes you just don't want your data traveling to a central location. It needs to stay in the edge. And regulatory requirements. I did talk about this, so I'll skip that a bit. But simply that it may be required to keep data for privacy or other locality reasons for regulations, to keep data in a geographic location that's close to where it was generated or within certain borders. So you can't always send it in. So let's talk about a real example, something that might be near and dear to the hearts of the other folks on this call. I think they're going to tell you a bit about computational storage. Let's say you're trying to make, because every presentation these days has to mention AI, machine learning, and 5G. So we're going to try to cover all those. So you're doing AI decision making with edge devices. Edge devices are sending in some kind of data. We mentioned a little bit, maybe this is automated cars that are driving and traffic signal coordination. The machine learning, the models for this may take place with massive data sets in the centralized data centers. But the resulting models from the training sessions are going to go out to the edge. And these are not that big. So they go out to the edge and they sit there. And this is where you make the decisions, called inference. So inference often happens at the edge because it's a smaller model. It's actually applying what you learned in machine learning. And that's where you want to make the decisions, as close to the edge. So these inference is happening now at the edge, very low latency to these 5G connected devices. The 5G devices are generally sending in small amounts of data, maybe very frequently, but it's small. So it needs low latency. It doesn't need a lot of bandwidth. And in the localized area, it has enough bandwidth. And that needs to be acted on quickly. And 5G, as we all know, is going to bring us a lot of this latency reduction so we can have many, many more devices. So this is why it's very important in this whole instance to have the storage you need for this at the edge. But this brings up some interesting problems. Edge data centers often are ad hoc. They're limited on the amount of power they have, the amount of cooling, the physical space, and sometimes serviceability. Just because they're distributed, they don't always have dedicated staff on hand. And this raises a lot of issues. The hardware selection may be limited. Maybe you can't buy an appliance because you can't get an appliance in there. Specialized configurations are often frowned upon. That is proprietary gear. And making the most of any resource is really important. So when you do put stuff on the edge, you put storage in the edge, it really needs to be multi-purpose. It needs to serve a lot of different applications and have a lot of different uses because you can't afford to put a different system in for every kind of load. So any storage solution you put there needs to be fast, needs to be multi-purpose, robust, because you can't have failures happen all the time. There's no one there to service it. Or if so, there may be limited serviceability in parts. It needs to be very flexible in implementation. And it needs to work on standard hardware and standard networks. It can't require a specialized network. It has to work with the Ethernet equipment that's there. So the question comes up, of course, does such a solution exist? And I'm here to tell you that I believe it does exist. That is LightOS from Lightbits Labs, who I work for. We are very high performance, believe in flexibility of hardware choices, of network. You choose the hardware, we bring the software, you put them together, and you get lower TCO while you're still getting high performance. It's software defined. So as I said, you bring the hardware, we'll bring the software. It's block storage, so it's at the base of everything. Block storage being at the bottom, we improve that layer the most, and then you can use it directly as block. You can put a local file system on it. You can put a distributed file system on it. You could put an S3 Minio object store on top of this. So the bottom solution, the devices, the block devices being really fast, low latency, high bandwidth, highly available, is going to improve the rest of the stack, all on standard infrastructure, which is very easy to deploy. And now you can scale your storage and compute independently. You don't have to put NVMe or other flash directly in your nodes where it's very much underutilized. You can have it be disaggregated, yet you still get the performance of NVMe, that is under 200 microseconds at load. We're talking millions of IOPS per node, 200 microseconds of read, 300 microseconds if folks are interested of write, and again, up to hundreds of thousands or millions of IOPS per node, depending on if we're talking reads or writes. And this lowers your TCO because you're going to get very, very high utilization out of your flash. And by the way, you get all this and we still increase flash endurance. The LightOS writes in a specialized way to the actual NAND media, that is in large blocks and sequentially. Any NAND media really likes this method, but QLC especially likes this method. So we aggregate the write performance over multiple devices, giving you still high write performance, low latency, and then we go ahead and increase the endurance of the flash by up to 5 times. This is a little bit what it looks like. Rushing through this, make sure I give other people a chance here. Standard servers on the left, standard TCP/IP networking in the center there, and then you have LightOS targets, which can be servers of your choice, or you can go ahead and buy the Super SSD from us, which is an OEM Dell 740XD. So very, very standardized hardware, standard networks, standard NICs. You don't need a Rocky NIC, you don't need any particular manufacturer's NIC. LightOS with NVMe over TCP works on any NIC, And then you can see we also fit into different environments, be they bare metal, with any kind of hardware of your choice. We work with OpenStack with a Cinder driver, as well as Kubernetes with a CSI driver. And I skipped, almost done here. But you don't have to give up what you're used to in things like all-flash arrays. Even though we're really, really fast, that's the technical term there, very, very fast. NVMe over TCP and our LightOS target still gives you thin provisioning on all volumes. So all volumes are thin provision, which makes it great for service provider networks, edge networks where you have multi-tenancy. We support line rate compression. So you can go ahead and if your data is compressible, you're going to save space and your data will compress, which can be turned on and off per volume. And you can also set your data protection level per volume. So if you need extra high availability, you can set it to a higher level of protection. Or if you need standard availability, you can set it down a little bit lower. Of course, volumes can be expanded and we have consistent response time, which is really important for edge locations. You have multiple different pieces supporting an application and you need those all to perform consistently. So we provide that consistent response time, better consistency using our remote volumes than if you're using local NVMe devices. And the environment is standard Linux. The NVMe over TCP drivers that you need are akin to iSCSI. That is, they're just part of the base distributions. If you use Red Hat or similar distributions, 8.0 and above, or SUSE, Debian, all of these things in the recent releases have NVMe over TCP drivers included, so there's nothing you have to load. It's just there. I talked about Kubernetes and OpenStack. We do all our management via an API and a CLI, so it's ready to be automated, ready to fit into the automated environment of your choice. We're not going to force you to use some kind of GUI. If you do want a graphical representation, we export all the data via Prometheus, and then we offer a pre-configured Grafana dashboard, or of course you can integrate into your own monitoring and management systems. And very close to lastly, I mentioned this QLC. If you want to go ahead and really reduce your flash cost, we do support QLC media, but offer up to 5 times the endurance on QLC because we're writing to QLC in the way it likes to be written to, and that is in large blocks sequentially. So it's an append-only model when we actually write down to the NAND. So this gives you high performance because we're striping over multiple devices. Generally if you use a 2U24, very common, you go ahead and stripe your write performance over up to 23 out of those 24 devices. And you're getting high aggregate writes. And of course, you also get very, very good read performance. And this allows for very high capacity, high density, which can also be very important at the edge. You don't have a lot of space, so you want to use the largest drives for the capacity you need, which means you can support today the 15.36 terabyte drives and the 30 terabyte drives that are right around the corner, or even larger. The point is you can put in whatever capacity drive is there, and we'll write to it in the way that it likes to be written to. So in summary, conclusion, LightOS meets the challenges of edge storage. We are low latency, which you need for the edge, high bandwidth, high performance density. Mentioned that already. You fit in large drives, and you can get as high as 16 gigabytes per second in a 1U server out of us. So very, very high performance density at the edge. It works on any x86 hardware and any Ethernet NIC. Supports high capacity, both TLC and QLC drives, and it does not require any special switch configuration. You don't have to change the config on your TCP/IP Ethernet switches. There's no special settings you have to do. If you already know how to do things like trunking, MLAG, and port bonding, all that stuff works for you however you have it set up. The knowledge you have is what you're going to use to set up storage on NVMe over TCP. And when I say it's very easy to deploy and easy to manage, meaning that you can go ahead and manage this remotely, and it can even fail in place. If you have drives fail, the system will go ahead and rebuild into spare capacity, keep on running, so that if you do have a service event such as a drive failure, your most common, the system will go ahead and rebuild into spare capacity from the missing drive, and it'll keep on running until you have the time to go replace the drive. And that is 5G. I had to say 5G again. That's it. Thank you very much.
Thanks a lot, Josh. All right, let me, next we'll have JB Baker doing this. JB, let me give you control. Let me get you to your slide here. Hold on 1 second. All right. You should have control, JB. It's all yours.
Okay. Let's see here. Okay, so computational storage at the edge. Well, both Josh and Mike have already mentioned some of this of why, but computational storage drives what this is pushing some of the compute functionality directly down into the drive. And what that does is it helps with the distribution of that function and parallelization of the tasks to improve the overall efficiency. So a couple of example functions here are going to be pre-processing the data, and the benefit there, you're going to reduce how much data you have to move to the host or move all the way up to the cloud from your edge, and that's going to cut down on your network burden. The second option here, second function that we're going to show is compression, and that is going to help with the storage economics for your edge, as well as improve the compute economics for your edge by reducing the burden on those CPUs to perform that compression function. I guess, there it goes, okay. So first off here on the data filtering, what I'm going to show is where we had filtering being done for RocksDB, and here we have 8 different instances running at the same time in a system. And what you see here with all these jittery lines is each color is the number of instances that are running. So from blue to green, all the way up there to the gray. And what you see on the top is with ordinary storage, without having filtering in the drive, there is a long time to move all the data back to the CPU for compute, as well as a lot of data that has to be moved. So think of the area under the curve as the total data bandwidth that was consumed. And then when we do the filtering in the drive down on the bottom side here, bottom graph, what you see is, yes, it's very high bandwidth for a very short period. So the total bandwidth consumed is significantly reduced. And the second thing that you see here is that as you've got multiple instances or multiple processes running, when you're doing the filtering down in the drive, they still all complete very, very quickly. When you've got ordinary storage without the filtering in the drive, they start to stack up and the latency starts to increase for performing each task. And I'll show you why that's happening here with the CPU side. Oops, sorry, one click too many. There we go. So here's another view of the same thing going on. And what we're looking at here is what % of the CPU is utilized. And so lower is going to be better. It's the same story though. The total area under the curve is how much CPU total processing was consumed. And with ordinary storage, what you see is that you get up to 4 instances running, and now the CPU is pegged. We're at basically 100% CPU utilization, and if I add any more tasks, all I do is end up waiting. With the filtering happening down in the drive, the less data is being sent to the host, so it's able to, it doesn't have to churn through as much to complete the query, and it's able to complete these much more quickly, and the CPU all the way up to 8 instances, the CPU never becomes the bottleneck. So, we're reducing how much pressure is on the CPU, so maybe you can buy a lower performance core or fewer cores, save on power, save on CPU there, as well as completing all the tasks faster, so you're able to handle that influx of data and run these processes all at the same time. Now on the compression side, what we see is that by doing compression, then of course you're going to improve your storage economics, and maybe 2x or more the effective storage capacity per gigabyte of physical storage that you purchase. Some types of data are not going to be very compressible, images, video, and pre-encrypted data. There's not going to be much compression available there. But for a lot of the data out there that's going to be stored into databases, or if it's web page or just log type data, that is going to be highly compressible. What I'm showing here is a paper that was written actually by our chief scientist back in 2015, where he and his students did a survey of different data types and how compressible all these different data types were. And that's the table at the top is sort of a summary. And then also just in our experience working with customers all over the world, we are seeing that they're reporting back that as long as their data is not encrypted ahead of time, that they're achieving anywhere from 2-to-1 to 5-to-1 compression with the compression engine directly down in the drive. So beyond just being able to store more data, what that's going to do is you can maybe increase the density per server, so taking up less physical footprint to achieve a certain capacity level. And then something else we've heard from customers is extending the backup window. So by increasing that density per server, they're able to delay the time in which they need to offload that data back to the cloud and do that backup. The other aspect on doing compression down in the drives is to help with the compute economics. And so with the compute engine that we put, or sorry, the compression engine we put into the CSD 2000 computational storage drive, we're doing the effective level of gzip or the zlib level 6 here, 2 gigabytes per second of throughput per SSD, right? So 2 gigabytes per second of compression, 2.9 gigabytes per second of decompression through that drive itself. And if you were to allocate x86 cores to perform that same function, it would take 47 cores to achieve that same level of compression. So that gzip compression would take 47 CPU cores, each running at about 10 watts. So you got another 470 watts just to perform that function that we're doing within the power envelope of an ordinary NVMe SSD. Lower levels of compression take less CPUs to achieve the 2 gigabytes per second of throughput, all the way down to LZ4, which can only take 3 cores to achieve 2 gigabytes per second, but you're not achieving the same level of compression there that you would with the stronger compression algorithm. So once again, you can buy fewer cores, you can get slower, a lower gigahertz core to run your same database applications. And I think that is everything that I had.
Thanks a lot, JB. Let me get Scott set up here. Scott.
Good morning, afternoon,
evening back
as well. This is Scott. Thank you for that.
Hold on one second, Scott. Let me give you control here.
No problem. Excited to kind of close things out. Definitely going to be highlighting some of what's already been talked to a little bit. The fun part of these multi-vendor webinars is you get to hear the same thing from multiple people in very different ways. It still shows the validity of what's going on. So it's all good. So I kind of took a slightly different approach to this and said, let's answer the 5 W's of how something like computational storage saves the edge. And I talk to it as saving the edge because there is no way to accomplish the tasks at the edge without technologies like computational storage and how they can be leveraged in solutions, for example, like the Lightphase product. So who needs the compute? What is computational storage? Because that's a term some people may not know and be near and dear to. Compliments of JB, he highlighted some of the techniques there. When is it needed? I think we all know it's now, but I'll have some fun with that. I'll showcase some of the examples of where it's being deployed. And then, of course, there's always the why you should care. So I took a different spin on it. Hopefully this will be an interactive way of highlighting some of the new technologies that's going on. So when I look at it from who needs compute, I see multiple different angles. And I have this graph empty for a reason because it'll come back to it and it'll show what's going on. But if I start going kind of top left around the architecture, you have smart cities and automation. So everything as we know and love near and dear to our heart, we call IoT. It needs the capability to compute locally and is generating so much data, there's just simply not enough ways to move it around. So those types of technologies are very capable of taking advantage of localized compute and highlighting kind of what Josh mentioned, there may even be restrictions on how it can or cannot be moved. As we go to the next one to the top right, this is a fun one. I call it extreme edge. So when you talk about serviceability, as Josh mentioned, what if it's floating in space? Now, granted, we have some issues with Starlink blocking out the stars and people complaining about our low Earth orbit satellites, but they're real.
they're true, and they need to be able to compute. I mean, think about the processing power we're putting into these 2-foot by 2-foot square satellites that are now taking over the low Earth orbit space. And the beauty of them is they go up and then they come back down and destroy themselves. So it's a short lifetime, but it has to have a lot of processing power. So you need low power, cost efficient, and flexible platforms to be able to deploy that. We already heard about autonomous anything, autonomous vehicles being one of the first, of course, that is coming in there. I think we have now FCC approval for at least 4 different companies to do drone deliveries. The drones have got to have some intelligence in them to be able to hit the right person's patio, front porch, or in cases of apartment complexes, finding their way down the hallways. I'm curious to see how that's going to work. And then you have your traditional data centers and as mentioned already, content delivery work as well. A lot of people are saying, well, hyperscale is still going to drive the market as far as consumption of storage. This is very true, but hyperscale is a type of technology and potentially a scale of a customer. They're still going to the edge. Everything is taking over the edge. And I'll even highlight how an example of the CDN technology is deployed today. So that's kind of the who. We'll fill in later with exactly how we're doing some of these solutions. What I wanted to do real quick is talk about the what. So what is computational storage? From a perspective of what NGD Systems is building, this is an ASIC-based product. So we did an ASIC-based controller because space is a constraint at the edge. So you need to be able to fit it into small form factors and manage those devices. So also going back to the comments from Josh, it needs to be plug and play, simple to deploy. So we built an all-in-one NAND controllable SSD with the computational storage resources built into it. So it's an all-in SSD product with modular firmware, supports the different vendor types. So to Josh's point, the vendor can choose what type of technology they want to deploy based on cost point, technology need, endurance requirements, and those types of architectures. And then we built into this particular product what we call in situ processing. So we actually built a drive OS, and it's kind of gotten a new nickname in the market as a server within a server. So each of our devices, as you plug them into your architecture, actually present themselves as a storage target or an actual subsystem. And it's a quad-core processor and even has hardware acceleration to be able to do things that we'll highlight in a minute around AI-like architectures. So there's a lot of opportunity for these technologies to drive forward and be plug and play. And again, keep it simple, stupid. The KISS principle is paramount in these types of architectures. So plug it in with NVMe and it goes and does the work. And so that's kind of the what is ours at a very high level. You can see there in the bottom right an example of some of the form factors that we have available today, and I'll wrap up with some details on those technologies. So when we think about when is it needed, I kind of use this fun slide as an example. So today, as highlighted already, we have physical space problems, we have power issues, scaling mismatches, and I've nicknamed it the bottleneck shuffle. So we have CPUs, we have DRAM, we have storage, as you can see by the 3 architecture blocks on the bottom left. But what the problem is no matter where we add performance, there's always a bottleneck somewhere in the architecture because you have a single processing unit talking to volatile memory that deals with non-volatile storage. And you can architect around those, you can compose them, you can stick them in many different types of platforms or arrays of architectures. But what we really need to be able to do is bring some of that processing power into the devices as highlighted as well previously. So computational storage brings the smaller footprint, the lower power, the distributed processing, and of course that ends as a result of faster processing power. So I put this future, past, present, so we have it today. It is deployable today. There are certainly challenges with it because it is more of a forward future looking technology. And the real problem is a lot of people get stuck in the past. It works, so I'm just going to keep doing it, and I'm going to just brute force attack it with existing architectures that are, quote, stable and secure, but not really looking at it from a perspective of innovation versus traditional. And so computational storage at the edge in architectures with all the technologies you've heard about already and what we're continuing to talk about is really driving the innovation forward and helping satisfy the need of a full edge deployment of storage architectures. So we've covered the who, we've covered the what, here's the when. As you can see now, I say it's today, and I full-heartedly believe in that as it's proven by a lot of the customer architectures that we've seen. So where is it deployed? I'm going to go back to this graphic here and highlight some of the architectures that we've deployed this technology on today. So we've done things like TensorFlow libraries running locally on the device. We've run Hadoop big data applications where we can run and offload different workloads from that application. We can run Elasticsearch, which is a very memory-centric platform, and augment its capability to do its work with computational storage devices. We've run all kinds of different database architectures, Greenplum, Mongo, Parquet, and even as we think more of the edge architectures, Azure IoT Edge, and I'll have a link at the end of the presentation where you can actually see that in action. And even AWS Greengrass, where we're now a certified provider of AWS Greengrass technology. So there's many different ways that all of these things play into each and every one of these market segments, and having an architectural design that plugs and plays, has flexibility, and can be modified to the point that Josh made earlier, where it's flexible. Once it's deployed, it can continue to change and evolve by having an OS on the device, allows you to continue to look at these different architectures in a new way. So I know we're kind of short on time, so I wanted to just point out some of the examples that we have available today from deployed customers. So an edge-centric, fault-tolerant, resilient database acceleration platform from VMware. An edge CDN where we worked with the customer to highlight what you can do from a CDN architecture. And I get a little bit into AI with some inferencing and machine learning related to different architectures used there. And as I mentioned, I'll wrap up with just providing a link to an Azure IoT demonstration. So knowing that we're a little short on time, I left the details for the follow-up because I'm a good marketing guy and I would like you to reach out and talk to me later. So first off, I'm going to highlight the VMware project. So they have this program at VMware called X Labs, and it's an innovation center which takes technologies that are no longer needed to be on a roadmap. They need to be deployed now. And they think of it from a 6-month deployment window versus a 3-year roadmap deployment. And so this program was put together by VMware and NGD to highlight the ability to deploy a computational storage inferencing and training platform using VMware Tanzu on a Greenplum massively parallel database in an edge environment. So basically we took a rack, a 42U rack of Greenplum database, because each server represented a node because there was only one quote brain or CPU in each of those architectures, and moved all of those nodes into individual storage devices. So each one of our NGD devices became an independent node, and we took a rack down to 2U, two 2U servers. This isn't edge deployment friendly, and because we're using VMware, vSAN, and these different architectures, it's fully fault tolerant, fully resilient, and has the capability of actually processing more efficiently than a rack level solution while being deployed in an edge data center, MEC, POP, whatever architecture you want to talk about. Now, I can't provide specific details on this because next week is the VMworld event where this is being highlighted, but that link will be live in the presentation afterward to allow you to register for the first ever free VMworld event. And it's an on-demand presentation where you can actually see the Tanzu architect walking through a demonstration of this architecture in action. The next one is talking about a CDN platform. So this was an actual customer lab. This graphic on the left represents what's called the Apache Traffic Control Platform. It's an open source platform provided by one of the primary CDN customers in the marketplace today. And they have this term that they love to call time to first frame. As mentioned, when you're streaming and you have thousands of people streaming, every one of us as a client in that bottom right of that picture has to go through some form of this architecture to get our content delivered to our screen. So we worked with the customer, and in this particular instance, we isolated it down to a singular instance called the traffic router, which is shown kind of dead center of that picture. And by doing that, we isolated a storage architecture piece of that edge device, which is a router, which has room for storage devices to be plugged in, but basically sat idle previously, migrated the storage needs that it had for network-based traffic routing lookups. And as you can see, the end result was that individual step became more than 50% more efficient with only 2 devices plugged in parallel. And that entire traffic control platform became 10% more efficient. And I've got a video clip on YouTube, on our YouTube channel, that actually walks you through the actual results screen for this particular graphic and representation. And so another one is talking about using AI and Stanis frameworks. So this is an example of how a neural network tends to be looked at from a host level perspective, and in general, that neural network shown as the dots and lines is always run on the host, and it extracts data from each of the devices. It runs it through its engine, and it post-processes that data out and pushes it into the final architectural design for whatever is being used by the customer. In our particular instance, we actually have a scientific paper that was published last month that's related to how we took this homogeneous Stannis framework and made it heterogeneous to work both in a host, which is x86 based, and an ARM-based processor on our device, so that we can offload portions or all of that particular framework into each and every one of our devices across a server. And again, data available on all of this is on our website or by reaching out to us, where we can highlight the performance gains. And in this particular one, we ran 4 different neural networks through the platform, and we ran multiple different inferencing engines through our platform, and we can share those details with each and every one of you after the call if you'd like. So what does that mean for you from a perspective of a technology deployment perspective? You have to look at it, oops, and of course the buttons are going there. You have to have an off-the-shelf product, in this case NVMe SSDs. You have to have form factors that work for the edge, including things like the new EDSFF form factor. You have to have capacities that work. That was even brought up by Josh, talking about 30 terabyte drives being available now. And those are, as you can see here, shipping in different form factors from our technology perspective. So off-the-shelf NVMe, high capacity, low power, and high density to support edge platforms. And QLC is, of course, important to everyone as we look forward. We'll be releasing those products here in the next 30 to 60 days at much higher capacity points, even than what we're showing here. So the capability to put computational storage and high capacity and ease of use at the edge is paramount in the technology and architecture that we've designed and deployed. So finally, I wanted to leave you with the link to the Azure IoT Edge deployment, where we actually deployed a full-on edge-ready solution, and walk you through a demo in that 14-minute video clip. And again, it'll be live after the fact. So thank you again for your time. Look forward to the continued conversation and looking through all the questions.
Thank you much, Scott. Let's jump into our audience survey question number 1. I'll launch this here real quick. And the question is how big of a problem will edge data be for your organization over the next 5 years? And this is a select one. And you should have a Zoom window that pops up. You can fill in those answers there. We'll give you a couple of minutes. And while we do that, we'll jump to the first panel question, which is what vertical markets and or use cases do you think as having the biggest issues with edge data over the next 5 years? And just kind of keep it to 1 or 2, or maybe the top one. We'll start out with Josh from Lightbits, then go to JB, and then to Scott. So go ahead, Josh.
Thanks, Mike. So I think basically the vertical markets that'll have the biggest impact is the example I gave, which is anybody who's doing AI decision making. So this might be a lot behind the scenes. Sometimes this is not necessarily consumers. This could be credit card processing. This could be making automated decisions, for instance, in credit card processing for fraud detection at the edge. We're seeing a kind of revolution there. Instead of, there were AI models being applied to historical data to kind of detect what kind of charge coming in looks like it's potentially fraudulent. And it would just look at data from historical records and then apply that to a model, and then you'd get a pop-up on your phone that says, oh, looks like someone's trying to charge for gas at this little gas station. Is this you? And you say yes or no. But what we're seeing is a move toward using real-time data, which is more along the lines, you can think of something like someone had a stolen debit card and it was used at an ATM, and then it was used 5 minutes later at a different ATM, and then it was used 5 or 10 minutes later at a gas station. And these events are coming into real time, being processed by different systems, potentially closer to the edge. And then the fraud detection is happening more in real time, thanks to new algorithms, but also things being done at the edge. So I think you're going to see anything that's AI decision-making based on inference from larger models processed elsewhere is going to move more and more towards the edge.
Excellent. JB, what are you guys seeing? I think JB's on mute. Let me see if I can unmute him here.
I did that.
Oh, there we go.
So yes, I certainly agree with Josh and Mike with what you've mentioned before about transportation and the telecom pieces. Another one is going to be, and this would tie into the electronic payments and fraud detection, but the financial technology and also advertising tech, where they're trying to serve very, very quickly in responsiveness to people, to their location and to what they're clicking on or viewing regionally. So, I think all of those are going to be aspects of the edge that are trying to make that real-time decision making and utilize and generating tons and tons of data.
Excellent. Scott, what are you guys seeing as the biggie? I mean, obviously, you highlighted several of them.
Yeah, definitely try to. And I think really what it comes down to from edge data is anything that does processing of raw data to provide a result is where we see the most benefit for the technologies that we've talked about today. So AI in any form of that, whether it be inferencing, machine learning, training, applies to edge data in mass for all of these different end markets and use cases. I think that's really, whether we like it or not and want to have to use the buzzword or not, we're all seeing use cases that revolve around some form of or method of being able to manage that raw data. So to the point, transportation is certainly one. Everybody's like, well, 5G is the savior of the world because we have so much bandwidth. But if you triple the bandwidth and you quintuple the number of devices on that bandwidth, you still run out. And I coined it to the concept of a freeway. Look at the 405 in Southern California. They add a lane every year, and every year it's still a traffic jam for an hour. Adding lanes doesn't help. Widening the path doesn't help. Finding ways of keeping the data local, processing the data, and making useful information out of that data, and providing those results back is paramount. And so I think it covers pretty much any market segment that needs to find a way to manage that influx of large data.
Excellent. Thanks, Scott. Let's jump to the second audience survey question. That question is, for those of you who believe that edge data will be an issue for your organization, what options are you looking at? And this is a select all that apply. So again, you should see that pop up in Zoom on your window. Take a couple minutes to answer that. And while you do that, let's go to panel question number 2. And we'll start with JB on this one. And that question is, current thinking regarding edge data and edge computing is that the amount of data will always exceed the ability to transmit it either to the cloud or to other data centers. Does your organization believe that that will continue to be true?
Yeah, definitely. I think Scott's analogy there is perfect with we keep adding freeways, we keep adding runways at the airports, but that doesn't help when you add just as many or more cars and flights. Of course, the flights have gone away this year, but so that's certainly going to be true. And that need to do pre-processing of the data, filtering it, keeping it local, managing it, and only sending the parts of the data or the results, the analysis of the data back to the cloud to stay within those bandwidth limitations is going to be crucial. So I think that's
Excellent. Scott, I think you already answered the question, but I'll give you a shot again. I guess we can figure in all the Zoom traffic that's going on out there too, right? That certainly makes things worse.
Exactly. I think another way to kind of put it in perspective is think about something like the movie with The Martian, where he sat there and had to communicate via the ASCII text. There's always a need where there's going to be a stretch of where that data is at and how you can manage it. You're always going to end up moving it back at some point, but it's going to be in different types of use cases like archiving and backups and stuff like that. So yeah, I did kind of answer 1 and 2 together, so I'll go ahead and let Josh have the floor.
I don't have a lot to add there. I mean, I agree. We covered, I think all of us covered this in our presentations. I actually like that airport analogy. If you think about what's happening, if you have a big jumbo jet, you need a really long runway. And so if you have a couple of those coming in, the airport, it might help the airport to add additional runways. But I think what we're seeing is we're going to see this huge influx of tons of little private planes. And these little private planes, they don't need the length of the runway. They don't need this giant runway. but they still take up space on it. And so in other words, the frequency of these little planes messes with the schedule of the big planes landing. And that's the same kind of thing you have happening at the edge. We're going to have tons and tons of little planes coming in. They still take a space on the runway. They don't need nearly that much length of runway that would represent bandwidth. They only need a little tiny fraction of it, but still putting themselves on the runway still blocks that runway from being used. So you absolutely positively need to keep spreading out. In that case, to extend the analogy, you need to keep adding airports. Those are your edge data centers, and add those airports as quickly as you can.
I think that's a really good analogy. Let me share the results of the second poll, and we'll go ahead and launch the third poll. The third poll is actually, what issues do you expect, or who do you expect can help your organization solve your data or your edge data problems or issues? This is again the select one. You guys should have it. It should be up on your screen now. Go ahead and take a couple minutes to fill that out. We'll go to the last panel question. And that question is, assuming the transmission will continue to be an issue, what are some of the most promising approaches to reduce the volume of data generated at the edge? Scott, we'll start with you. I know we've talked about some of these things, but if you just hit kind of one or two things, and we'll go to Josh and then JB to finish it up.
Yeah, it's interesting. So the transmission will, as you mentioned, will always be an issue. There's nothing that we're going to be able to do to resolve that. We'll get beyond 5G. We'll create all kinds of new architectures to be able to transmit data. It's a matter of your point, reducing the volume of data. And I wouldn't put it so much as generated. We're going to generate more than we know what to do with. I think it's about how we manage how much of the data generated we move. So we're going to continue to create more and more connected devices, more and more connected architectures, and drive those things forward. But things like computational storage or more intelligent storage systems at the edge, where they can do more real work in a smaller environment, say the trunk of a car or a satellite in space, is paramount to success. And that can be done with computational storage. There's other architectures out there that are looking to solve some of that. And you'll be able to continue to see those efforts driven by organizations like SNIA, NVMe, and other standards bodies as well, to help make it easier for all of the attendees to actually deploy these solutions as well.
And this is Josh. I'd have to be boring here and just simply agree that we can't. You can't send all the data at the edge for centralized processing. So, but at the same time, you don't necessarily want to reduce the data coming in, because it's infinitely useful. So that decision making, that analysis, that reduction, it needs to be done at the edge. So, and that's why you see the data from Forrester and from Gartner saying that most of that data is going to be at the edge, because it needs to be generated. It is useful. And the NVMe storage in general has kind of solved, or I think it was Scott saying, you play the game of move the bottleneck. The storage isn't really the bottleneck anymore. CPU and memory bandwidth starts to become the bottleneck. So you have to move those things around, and we'll process the data at the edge, and that will end up resulting in a lower amount of data going into centralized, but not because it's been reduced really. I mean, it has been data reduced, but not because it's not coming in from the devices, simply because you don't need to send as much in.
Yeah, I basically, yeah, I gotta agree with those guys too. You're definitely not going to be reducing the volume of data that's generated. That's just going to continue to accelerate. But it's, rather than shipping all of the raw data, it's shipping information. We're going to have to get to sending the abstracts or the cliff notes for those of a certain age back to the data center, instead of sending the entire volume of all of the data. And then, and even there, we can expand and send some of the raw data in addition to the information through compressing the data and identifying which is going to be most relevant, and then compressing that to take the least bandwidth, make the most efficiency out of that network that we can get.
Very good. So let's, with that, jump into the Q&A session. I'll start with questions out there. The first one's pretty much focused on Josh, and that is, I'm going to throw something in here. Is LightBits open source? Is there any performance benchmarking tool for LightOS?
So LightOS itself is not open source, although I would want to add that LightBits, the company, has been instrumental in open source for NVMe over TCP, and that we wrote most of the code for the NVMe over TCP client and initiator that's in the various Linux distributions. We contributed that to kernel.org. So very strong supporters of open source and standards. We also submitted the open source NVMe over TCP target. So we participated on the standards board for NVMe, very much believers in open source and standards. However, the target itself is closed source, and that it does some of the special work. So that is software that we want you to buy. And as far as a tool, you can use the benchmarking tool of your choice. Very common to use FIO to go ahead and benchmark our volumes, as well as VDBench in a more enterprise style environment. And so you can use the tool of your choice that you would normally benchmark, like even a regular SSD.
Excellent. All right, our next question is computation, and this one I'll send to Scott and then to JB, and that is computational for the edge, computational storage for the edge. Sounds very useful. What small form factor does computational storage support? As edge compute also needs to also be small, light, and low on power. Does it support M.2 and/or E.1s? I'll start with you, Scott, and then we'll jump to JB.
Yeah, so there's definitely a need to have these smaller form factors for the space-constrained environments. That's one reason, for example, NGD went with the ASIC-based solution. The M.2 is certainly used today, even in the data center scales, with companies like Microsoft through the OCP platform. The EDSFF, which is the E1S, E1L, and other form factors, are starting to take over and replace that M.2, and they're very paramount for that. We're proud to be a provider of those solutions today. There are some other computational storage solutions that can also support those smaller form factors, knowing that they need to be available for deployment in edge-friendly environments.
Very good. JB?
Yeah, so for today, ScaleFlex, we support the U.2 and the half height, half length add-in card, which are still the predominant form factors for deployment of PCIe or NVMe class storage. We will be enabling the E1S and the other EDSF form factors that are coming out in our next generation of products.
Excellent. All right, next question. This is another one for Josh, and that is, can the LightBits SDS support computational storage at the edge? This one kind of crosses all three vendors, I guess.
I mean, for folks out there, we were actually talking about that before the webinar started. These devices tend to be, if they're NVMe accessible, or have an NVMe PCIe interface, there's not a reason why. So today there's not an integration that we can use the two together, but it's certainly a possibility.
Very good. All right, our next question is, any OS or hardware requirements for LightBits Labs or NGD? And I'll leave that also to JB, but let's start again with you, Josh, and then we'll go to Scott and then to JB.
So yeah, sorry about that, I was on mute. From a perspective of OS or hardware requirements, our platform works with pretty much any implementation that you want, x86 or otherwise. Internally, our device is an ARM-based solution, so if you're not, if you'd like to offload, if you will, the compute into our devices, there's an opportunity to cross-compile, or we provide the tools to do such work. So it is fairly flexible in its deployment. As a base product, it plugs in and acts and looks like an NVMe device, so it has no issues with just being used as a standard storage product as you implement it as well.
And for LightOS itself, for the initiator is included in most of the current Linux distributions, starting with Red Hat / CentOS 8.0 and above. It's also available in SUSE and OpenSUSE and Debian. So the initiator is available in most Linux distributions. And if you have an older kernel, an older distribution, we can do sideload drivers and compile them because, as someone asked earlier, The initiator is open source, so you can go ahead and get that driver for older versions. On the target side, we are a set of RPMs that you put on top of a base CentOS or Red Hat distribution. So that's basically what we like to go on top of on the target side. And hardware requirements, it's x86. No special NIC is needed. And NVMe drives. There was a question on, do we support SAS and SATA? No, we don't. You do have to have NVMe-based drives on x86 systems and any NIC.
Very good. And JB, how about from your guys' perspective, any OS or hardware requirements for ScaleFlux?
Yeah, any Linux OS. We don't support Windows or VMware. And then from hardware, industry standard slots. So any U.2 bay that has connected with the PCIe, and any PCIe slot that can support a half-height, half-length card.
Very good. Skip to the next question, and that is, and then we'll go to the last one. It's what is the typical amount of data on each edge device? Is it gigabytes? Is it terabytes? You know, I'm sure this is going to vary on the use case, but kind of what are your guys' perception on that? Why don't we start with you, Josh, and then go to Scott, and then to JB.
The typical amount of data on each edge device. That's a very difficult question to answer because it's going to vary wildly. So let's say you were doing medical imaging with a 3D CAT scan. These images can be in the terabytes each. Very easy for them to be a terabyte size image, depending on the resolution of the scanner. And then if you wanted a process to go ahead, like an AI process to examine that file and look to see if this was, you know, a chest X-ray or a chest 3D scan, if there's cancer, you want that at the edge. So then we're talking in terabytes. However, I don't think there is a typical amount. If you're talking about data coming in from my Apple Watch or a Fitbit on my heartbeat and patterns and whatnot, these are tiny little things sent in frequently that are going to only be in the, you know, megabytes or less per hour. So I'm not sure there is a typical. It's going to be very application specific.
Yep, absolutely makes sense. Scott, what have you guys seen as far as typical data sizes for edge?
No, I would agree. It comes down to which deployment you're looking at, where you're putting it, right? So you can have a POP, which is a point of presence, which is a street corner based data center classified as the edge, or you can have the extreme edge, which is anywhere from a base station to the trunk of a car. And so the size is very relative. I think the biggest piece of it, to Josh's point, is the size is much larger than most people are thinking. An example of a deployment in a car trunk today is 32 terabytes of storage in the trunk of a car, and that survives 1 day of traveling around in that vehicle. And they have to offload, move, delete, and reset over 32 terabytes of data in each car each night with what we classify as ADAS level 3 today, let alone when we get things like ADAS level 5 and full autonomous. We're going to be generating huge amounts of data in very small spaces. But again, it's relative to the form factor and the location of that edge that you're talking about. And that's a whole nother conversation about the definition of edge.
Yes, absolutely it is. It's true. JB, I assume you guys are seeing something similar to this from your perspective?
Yeah, I mean, not much to add there in terms of, because it is all just what aspect of edge are you looking at. I guess, you know, what I do see is that when we get into, say, the drive level device, as opposed to thinking of the edge, you know, the entire edge data center or POP, as Scott mentioned, we are seeing that capacity is increasing just to drive the right economics of the performance per terabyte and the capacity per cubic centimeter of space, and that, you know, 4 terabytes is kind of the minimum or the high runner today, and rapidly moving to 8 and higher as we transition from TLC to QLC over the next couple of years. Yeah.
Excellent. Another question for Josh. I think it's for Josh, and that is, what type of RAID is supported? What is elastic RAID?
Thanks for the question. I appreciate it. So LightOS Inside each target server uses what we call elastic RAID. This is a RAID that shrinks and expands automatically per the number of drives. It is a +1 mechanism. And inside a large server, you can actually have two groups of +1s. So if you had 10 drives, it would operate as a 9+1, which sounds really weird for a lot of purists out there. They're like, oh my God, how can you have an odd number of data drives? It doesn't really matter. Elastic RAID is, that's why it's called elastic. It can do that 9+1. If you have a drive failure, the protection reverts to an 8+1, rebuilds any missing data and only the data that was written to the drive into the spare capacity. And now it can keep running forever, still protected as an 8+1, as long as you have capacity. And then if you go ahead and replace that drive or even add new drives, and it goes up to 12 drives, it would be an 11+1. So that's how we protect against drive failures inside the system itself. And then to protect against target failures, we use replication. That was the one that is set on a per volume basis. So you can either replicate 1, which is no copies, 2 or 3 times, depending on your need. Of course, then people might be saying, replication, 2 times replication, it uses so much storage. But if you have compressible data, if you get a 2-to-1 compression ratio, then your basic 2x replication is a wash. So you basically get high availability, protection against a drive failure, protection against a host failure. And on drives, it can be a fail-in-place system. So you don't have to service drives right away. You can keep running with protection as soon as the partial rebuild is completed.
Excellent. And then the last question, this one is directed at JB, and the question is, are you using FPGA or ASIC-based controller? If it's FPGA, how do you balance power and performance for edge computing?
We do use an FPGA currently. It is a smaller FPGA, a lower power one. So we're not running in a 100-watt each or FPGA or anything. We're keeping the power of the drive well within the 25-watt envelope for U.2 and low profile add-in card. And what we see in comparison to ASIC-based NVMe drives is that we're within a watt for typical performance. So we really haven't had to make a specific trade-off there other than choosing a smaller, lower power FPGA, which puts some limitations on how many additional computational features we can put in, but we achieve performance that is on par with NVMe SSDs on reads and exceeds their performance on random writes at a same power level.
Excellent, very good. Well, thank you again, everybody, for joining our webinar. Thank you, JB, Josh, and Scott for being panelists and sponsoring this webinar. Again, we will send out a link to the recording and a PDF of the slide set on Thursday. So with that, I thank everybody for joining us and have a great day.
Thanks, Mike.
Thank you.
Everybody take care.
Thanks, guys.